Everyone, so we are in our second example of creating the equation of a polynomial function, and in this case I'm actually going to use the exact same function, or same kind of, I guess, restrictions that was on the previous problem, except instead of a third degree, it is now a fifth degree polynomial. Alrighty, so we know, again, what our general form is going to look like. There's going to be some unknown constant out in front, and then our linear factors are going to be x minus 3, x minus 1, and x plus 6. All right, that doesn't change. Okay, what does change now is, well, some of our roots are going to be repeated because given this nature of the problem, this has to be a fifth degree polynomial. But what I've drawn so far is a cubic, a third degree, right? Because it's one of these, and one of these. So I need to do a little bit of playing around with it to make it a fifth degree polynomial. And we have a couple options here. One thing that we're going to do is let's suppose I could square that and square that. Ready? So now it's a fifth degree polynomial because I'll have two factors right here, 3, 4, and then 5 factors. Now, you could also have just cubed one of the factors, and then that would have also worked to make it a fifth degree. I'm going to do that in the second video just to see what would make it, how it would affect the graph. Okay, but in this scenario, this is what we'll go with. In this video, we'll go with squaring two of the factors. But this is going to be pretty much the same as the last video. So we squared that now, and we want to make sure that when we put in 0, we end up with 300. So that's going to be a times, okay, so I have 0 minus 3, and I'm going to square that. So it's going to be 9 now, times 1, and then times 6. Just like in the last video, I'm going to divide everything by 6 to make my life a little bit easier. That'll cancel out there, and I'll get 50 equals a over 9, and I'll divide both sides by 9, right? Okay, so this is what this function looks like. Oops. So we have p of x is equal to 50 over 9 x minus 3 squared times x minus 1 squared times x plus 6. Alrighty, but now I also want to sketch this graph, because why not? So I'm going to get my x-intercepts in place, like so, and my y-intercept. So my y-intercept still is at 300. My x-intercepts are at, oops, that should be 1 and 3, and then negative 6 back here. Maybe I won't put it so far back this time. All right, so again, I'll plop down my points. There, and there. And so on this one, well, okay, at x equals negative 6, so I'm going to go from the y-intercept and go to the left this time to start. It needs to go straight through the x-axis, because again, this is just a linear factor. That is not repeated at all. So it just goes straight through. And the reason it looks like that is because if we were to just look at this piece right here, that the function like y equals x plus 6 is just a straight line. And so when I look at this part right here, it looks just like a straight line. Okay, now if we compare / contrast that with the next factor, which is x minus 1 squared, the graph of x minus 1 squared is a parabola, specifically with its vertex at 1, 0. So that's why when you have a repeated root where it's repeated twice, its multiplicity is even, that is, it has that behavior where I said it like balances off the x-axis. And so what's going to happen here is going to come down to 1, and instead of going straight through like that, it'll come down and then bounce up like so. Now, what's going to happen here? Well, it has to come back at some point to hit the x-intercept at x equals 3. So of course it has to come down like so, because this one is also squared. It will also bounce back up and end like that. And this actually looks just like our typical fifth degree polynomial, because it has 5 directions: 1, 2, 3, 4, and 5. We also know that this is the correct shape because, again, it is a positive x to the fifth. So meaning if I was to expand this again, I'll get positive 50 over 9 x to the fifth, and so on. So since we have a positive leading coefficient, it's positively oriented, meaning the positive end of the graph ends up in the positive direction. Alrighty? Hopefully that helps. And again, we're going to look at a second way to do this problem in the next video.